I'll begin with a word of prayer. All right. So, Heavenly Father, we thank you for this day. I thank you for the students. Just ask that you just help us to use the time that remains wisely for your glory, Lord. And I pray. Amen. Okay, so to start with, let me just go through the quiz that we started with. First of all, the definition of a series converging is that the limit of the sequence of partial sums converges, right? So, most briefly, the limit as n goes to infinity of the sum k equals 1 to n of a sub k is equal to L. This is what it means for the series to converge, right? To get credit here, you must meaningfully have said something about the limit of the sequence of partial sums, right? I don't give any credit. If you have like infinity here in the limit, I won't even give partial credit. All right. But anyway, that's it. Problem, any questions? Okay. Problem 2, as I forecasted, is telescoping, right? So if you do the partial fractions on this expression, you can get that 1 over n plus 2 times n plus 3 is 1 over n plus 2 minus 1 over n plus 3. And then because I used n for the summation variable, I decided to use k for the kth partial sum. Yeah. So the kth partial sum is sum n equals 4 to k of this with the partial fractions. And then if we put in n equals to 4, we get, oh man, come on. Seriously? Ay, ay, ay. 6th, 7th. 7, 8. That's okay. And so the answer is not 1/4, it is 1/6. Yeah. So for those of you who were thinking that you got it wrong for 10 seconds, you should think more highly of yourself, you know? I make mistakes, right? So there you go. 1/6 is what that one works out to. Yeah. Again, that's a telescoping series. It converges to 1/6. Problem 3 was a sum of geometric series. So to make this step, here I'm using steps below, really. In other words, when I make a step like this, I like to tell students I'm taking out a logical loan. All right, and so whether or not I can pay that back depends on after I, work through the details of the series that I have on the right-hand side. If they actually both converge, then this was a legitimate step. If after you do this, one of them's infinity and one of them's minus infinity, well, that step is not allowed. All right, but this one is allowed because, in fact, after you clean this up, you can see that the first term gives us a geometric series with radius 5/9. And the second term is geometric series with radius 1/2, both of which converge because the radius or the ratio is less than 1 in absolute value. And so whatever that works out to, I'm not sure. I haven't finished the arithmetic here. That's what? 4/9. So 7 times 9 over 4 plus 8 times what? 2, whatever that is, 63 over 4 plus 16, also known as 127 over 4, I guess. So, good enough. So that converged as well. All right. Incidentally, actually, these are the two main cases that we can calculate the sum of the series on your next test. Either it's a telescoping, or it's geometric, or something close to it. That's pretty much it in terms of direct calculation, right? Otherwise, we're using convergence divergence test, and we're making indirect arguments. Okay, with that, let us transition over here to the in-class exercise portion of today. See if sum k equals 1 to infinity of k over k cubed plus 1. So I've got a half plus a ninth plus 3 over 28. I would agree, but I would trade this with a what's written and then also plus dot, 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 dot. Give this a name. Let's call it S. Let's say S equals to that, yeah? The plus dot, dot, dot is important, right? Those first three terms are not the series. They're just the third partial sum. So what's our intuition here? Up converges. I think that's reasonable. And what did you guys do? Looked like you went for the direct comparison to p equals 2. Oh, no, no. True, but useless. True, but useless. I mean, this right here is comforting, but irrelevant. In the sense that if the kth term goes to 0, does that tell us about the convergence or divergence of the series? It says it's possible. It doesn't guarantee anything, though, right? I mean, if the kth term goes to 0, that means the series might converge. It might diverge, too, the harmonic series being the example. So therefore, this converges by comparison theory. Comparison theory is not a thing that we had. So this won't do. This won't do. How about this? This is good. Your heart's in the right place, but what you need to do, it converges by direct comparison test against the convergent p equals 2 series. Right? That's the actual logic here. Your inequality shows that the p equals 2 series is larger than the given series term by term. And the p equals 2 series converges, therefore, by the direct comparison test, which you can abbreviate DCT if you like. Right? If you're like, I don't like abbreviations, I insist on writing direct comparison test. Are you going to take off points? No, I would not. If you wrote out direct comparison test, I would not take off points. But none of you ever asked me this. But you could, direct comparison test, right? Any questions? So, I mean, one of the first orders of business is you need to know the names of the tools that you're working with, right? So it's not comparison theory, it's the direct comparison test. Because comparison theory would include two different tests, right? I mean, there's two different tests which are in the comparison theory. There's what? I mean, in some sense, all of these are comparison theory, right? In some sense or another. I mean, I don't know. But when I think comparison theory, to me, it most directly brings to mind, say, direct comparison test, or what's the other one? The limit comparison test, right? So you should try to convince me that you're thinking about the right one. When you write something like comparison theory, it's very vague to me. All right. All right, so let's see, problem 2. We got what? 1 over the square root of 2, 1 over the square root of 3. I thought it was 1 over the square root of 4. Oh, square root of 4 is a half. Very good, okay. Again, you know, plus dot, 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 dot. And let me just give this thing a name for the sake of not writing it again. Minor complaint. And you said it diverges. Okay. Why? And what was the logic? Who was in the group? What were you guys thinking? I mean, it looks like they're going to 0. So why do you think it diverges? I mean, you're right, but why? Yeah. Yes, this is, okay, yeah, I totally agree. This is like the p equals 1/2 divergent series, right? Now, there are various ways to prove that. I mean, excuse me. I think perhaps a good way to do it, though, would be limit comparison test, right? We could use limit comparison here. let's try limit. So usually if your intuition is that it diverges because it's like something, often that whatever it's like is what you should try the limit comparison test with. So what's limit comparison test say? So we're going to look at 1 over the square root of n plus 1 divided by 1 over the square root of n. Limit comparison against 1 over the square root of n. Well, to be fair, sum n equals 1 to infinity, 1 over root n, yeah? So I look at the quotient of a sub k over b sub k, right? And I do the math. So this simplifies to the square root of n over n plus 1, yeah? Which if you divide the top and the bottom, just do some algebra here. This is the square root of 1 plus 1 plus 1 over n, which goes to the square root of 1 plus 1 over 1 plus 0. In other words, the limit, this is 1, right? So what would the limit comparison test said? It said if you take the quotient of your given series and your comparison series, and that quotient works out to a positive, we're comparing positive series, right? So it's going to work out to something positive. If it works out to something positive, then what's it say? It says that the fate of the two series is shared, right? So therefore, by limit comparison test, your given series here diverges. And so to be clear, this is as n goes to infinity, right? Hence, by limit comparison test, S diverges. If I hadn't already said I'm using limit comparison against the 1 over the square root of n series, I should say that in the conclusion statement. Somewhere or another, the words should be appearing in your solution. I am using limit comparison test against the divergent p equals 1/2 series. Like, this should be part of your statement. You should say what you're doing. Don't assume I know what you're doing, all right? Sometimes professors will say something like, you should imagine you're trying to explain it to your grandmother. It's like, I don't go there, but I mean, you should imagine you're explaining it to somebody in the class who doesn't understand as much as you do, all right? Like, don't assume that everyone knows what you're thinking. You have to write it on the page. You have to make clear and explicit your thoughts, all right? You're like, but I'm wrong, and I don't want you to know that, so if I write too much, then you'll know that I'm wrong. I know that. That's why I want you to write your thoughts. So, well, that was kind of oddly timed. No, the reason we're going through this is so I hope you have a better sense of what's expected of you, okay? Problem 3. I better move it along. There's no way we're going to get through all these. Problem 3. Oh. I mean, not wrong, but I think, and I don't often encourage this, but I think in a problem like this, he's got a case of the giggles out there. Maybe decimals are helpful in this problem. I don't know. But that's fine. Again, my, plus ... complaint would be the, that's the series now. And I'll give this thing a name so I can refer to it. You say it converges. Huh. See, this is the trouble with intuition, is it can be wrong. So this one, no, I do not think this converges. I think, I'm pretty sure this diverges. Let me see if I can explain to you why. Yeah. Because we're looking not at the limit of the nth term in the series, we're looking at the quotient of the given series nth term against the nth term in the divergent p equals 1/2 series. So we're using the limit comparison test. We're dividing the given series, which is 1 over the square root of n plus 1, by 1 over square root of n. So this is like, in the lingo of the direct comparison test, this is like the a sub n over b sub n. Or maybe I used k on the day we did that, you know. So what the limit comparison test said was that if the limit of the quotient of those two works out to something positive, then however the AN series converges, the BN series converges, or vice versa. If the AN series diverges, the BN series diverges. This is the limit comparison test. So, how about this? So, what can we say about 2 and cosine k? I can tell you this. 0 is less than or equal to 2 plus cosine k. Well, oh yeah, fine. 2 plus cosine k is less than or equal to what? Actually, 0 is, I can be greedier than that. 2 plus cosine k, what's that look like? Let me restate this question. Cosine k is, at worst, smallest cosine k can be is what? -1, right? The largest cosine k can be +1, right? So if I take 2 plus that, that's going between 1 and 3, right? And then, okay, great. Divide that inequality by the square root of k plus 1. So 1 over the square root of k plus 1, right, is less than or equal to 2 plus cosine k over the square root of k plus 1 is less than or equal to 3 over the square root of k plus 1. Now, you know, to critique my own writing, part of this writing doesn't matter. The upper end, right, the 3 and the 3 over square root of k plus 1, true, but irrelevant. All right, irrelevant. What's mission critical here is the lower inequality, right? So right here, this right here, so thus S diverges by direct comparison test to divergent P equals 1/2 series. So I would encourage, let me just fix my solution so it's even better. So what I'm trying to say is this upper part doesn't matter a bit. The thing here that's important is that the given series, term by term, is larger than this. Oh, and I guess I'm still using something else, right? Is this p equals half? So what am I using at the moment? Yeah, using problem 2, right? Okay. Not p equals half series, problem 2 series. Because in problem 2, we proved that 1 over the square root of n plus 1 diverges. That series diverges, yeah. Honestly, if this was a problem on the test and you said that S diverges by direct comparison to the divergent P equals 1/2 series, I probably wouldn't even take off points, because one of the things I'm trying to get you guys to get to is the insight that, like, the intuition here that this diverges because this is like a P equals 1/2. I mean, people who are more sophisticated than us would just say this is a P equals half series. Like the fact that this is shifted. I mean, this is just the P equals, this is the tail, right? This is the tail of the P equals half series, is it not? You could rewrite this as the sum, let's say m equals 2 to infinity of 1 over the square root of m, right? So this is, by the way, the other way you could have done problem 2. The other way you could do problem 2 is simply to reindex the series and recognize that it is the tail of a divergent series, which is therefore divergent. This is another theorem we have to work with, which I have never written on the board yet. My bad. But we've talked about this a little bit. You know, the tail of the series behaves as the series, right? If the series is convergent, any tail of the series is also convergent. And if the series is divergent, any tail of the series will also be divergent? What's the tail of a series? It just means instead of starting at 1, or instead of starting at 0, you start later on. Right? So if you can recast a given problem as the tail of a known problem, that's also another way to directly solve something. I think that's actually an easier argument here if you see it, right? But limit comparison is, limit comparison test is very nice. It solves a multitude of problems, and it's very concrete. This thing I wrote at the top of the board here, reindexing using M, that's a little bit more sophisticated. But I think that many of you could see that as soon as you write down the first 3 terms, right? See, it's just square root 2, square root 3, square root 4. It's just the p equals 1/2 series starting where? Not at 1, but at 2. So I'm really going from your work in number 1 to write this right here. Does that make sense? I hope it makes sense. Oh, hey, wait a minute, did I not, nobody got this one? Aw, shnikes. What do you guys think? I guess I'm on my own then, huh? You think we shouldn't do this one? What do you guys think? What's the right tool for the job? First of all, let me do the first couple terms. Natural log of 1/1 plus natural log of 2/8 plus the natural log of 3 over, we got 27. Of course, so this is just 0. But it seems like there's hope. Seems like there's hope for it being, yep.
Remember too, if it goes to infinity, why wouldn't it go towards 0?
Are you asking me why this doesn't go to 0? This is not the series. This is the quotient of the series 1 over the square root of n plus 1 against the p equals 1/2 series. We're using the limit comparison test. It is true that if you just look at 1 over the square root of n plus 1 as n goes to infinity, that goes to 0, absolutely. And that's lovely, but it doesn't tell us anything because, again, the nth term test, when the nth term goes to 0, that just tells you that the series might converge. The only time the nth term test, oh man, you guys use the red marker. So this was my, I cannot see. Can you turn the camera over here? So this is a very nice answer, but this is very good. But indeed, this diverges by the nth term test. So here, S, I'll have to rewrite it. I'm sorry, guys. What you've written is good. It's oh man. Inverse tangent of 7 plus inverse tangent of, what is it? 11 plus inverse tangent of, 8. I went straight from 0 to 2. So that's the first 3 terms. And what it says here, I know you may not be able to read it, but it's not their fault. It's just marker. As n goes to infinity, inverse tangent of n squared plus 7 goes to pi over 2. Therefore, this is a divergent series by the nth term test. Right? So that's pretty much the only kind of problem where the nth term test is, definitive. Otherwise, it's just like a step on the way of going, oh, I still have more work to do. All right? It's like when you're working out a limit and you get 0 over 0 or infinity minus infinity. You're not done. You have more work to do. Now this one here, what do you guys think? Problem 4. I mean, maybe limit comparison test will work. What would you compare it to, maybe? I might try. I'm not sure this is going to work, but we'll try it out. We'll try limit comparison with, I don't know. Let's try p equals 2. Want to try p equals 3? I want to do p equals 2 series. So we got to look at natural log of k divided by k cubed divided by 1 over k cubed, k squared rather, which is natural log of k divided by k, right? This has what type? The limit comparison says take the limit as k goes to infinity, right? This has type what? I mean, as I look at the limit as k goes to infinity, I'm looking at log of infinity divided by infinity. I mean, that's infinity over infinity. Extending k continuously, I can apply L'Hopital's rule. So we get natural log of k over k goes to what? 1 over k over 1, which is 1 over k, which goes to 0 as k goes to infinity. Oh, man. Wait a minute. Well, this is the wrong class. So I'm looking at my abstract algebra notes. This will not help us. Theory of field extensions is not terribly relevant to what we're doing. Let's see here. Limit comparison says, theorem 12.3.7, if a sub k over b sub k goes to L and L is positive, oh man, if L is positive, well, look at that. What does this mean? It means, oh, it didn't work, we give up, right? Wrong. You don't give up, you just say, didn't work. See, because it worked out to 0, which means limit comparison isn't going to do it here. We need a different tool for the job here. What's the right tool then? Do you guys know? You can say, well, I'm going to try limit comparison with something else. Yes? Integral test sounds like a winner because natural log of x dx over x cubed, right? I think that integration we can do with a what? Is it integration by parts? I mean, if we have, maybe it's integration by parts. Let's see here. So if I trust Liate, u equals the log x, dv is dx over x cubed. So minus natural log of x over x squared, I think, or 2x squared. Integrating it 1 over x cubed gives me minus 1 over 2x squared. So then plus 1/2 integral of v du, which in this case would be dx over x cubed, I think, because I get x squared from minus 1 over 2x squared from the v, which I've canceled the minus in the integration by parts to give me the half out front, and the du is dx over x, which is why I have x cubed there. Yeah, I think this is it. So integrating gives me minus 1/2, or 1 over 2x squared log x, minus 1/4 over x squared, 1 over 4 times 1 over x squared, plus a constant. Yeah, so we can do the integral of the corresponding function by integration by parts. Yes, so I'm not going to write it all out because we have other problems to finish today, but if we continue with integral test, we can do this one. So that's at least a way to do this. There might be a more clever way that, to me, integral test is a weapon of last resort. Because in order to use the integral test, we still have to do what? look at f of x equals log x over x. We have to prove it's continuous, positive, decreasing. We have to calculate this integral. By the way, my intuition here is that log grows slower than k, right? So because log grows slower than k, maybe there's a direct comparison that could be done here. You probably could argue this, guys. So I bet, thinking about this for just a second, I bet we could do direct comparison to p equals 2 series to get convergence, because it's smaller than the p equals 2 series. Something that I just did here, which I don't think is immediately obvious, is why is the log of k smaller than k? Is that clear to you guys? Why is that true? If it's not clear, you should think about how to prove that. I can show you a graph of why it's true. Here's log k. Here's k, continuously extended. Log k always grows at rate 1. Natural log grows at rate 1 over k. And so because k starts out ahead of log k, it stays ahead forever and ever because the log k grows slower, so it can never catch up to k. There's an intuitive proof that log k is less than k. You could do better. Anyway, shut up about that. Problem 5. 2. Very good. And then so, to be clear, a formula like this is more, sort of, I don't know if it's more carefully written, but, to be clear, we're looking at that. We're doing twice n factorial, and in contrast, the denominator is 2n factorial. So I've got a sub 0 is 2, because it's 2 times, this is 2 times 0 factorial divided by 0 factorial, right, which is 2. And then we've got 2 times 1 over 2 factorial, which is 1. Very good. A sub 2 is 2 times 2 factorial, which is 4, divided by 4 factorial, which is 24, which is 1/6. Very good. Converges to 0. I don't know what it converges to, but I do think you're right that it converges. And let's see here. What's going on? You've got, I think it converges. You have, I think we're trying to use, so before we do this, right, it's helpful to just say, consider ratio test. Let the reader know what you're up to. Consider the ratio test, right? So then you're looking at a sub n plus 1 divided by a sub n, because that's what the ratio test is about. And then algebra happens. This might be right, but for the purposes of time, I'm going to just redo it. So, sorry guys. Okay, so a sub n divided by, was it a sub n plus 1 divided by a sub n, or is it a sub n plus 1 divided by a sub n? Did I just say the same thing twice? A n plus 1 is on the top. A sub n plus 1 divided by a sub n. Very good. So that is 2 times n plus 1 factorial divided by 2 times n plus 1 parentheses factorial divided by, times the reciprocal, which is 2n parentheses factorial divided by 2n factorial. So what you're looking at here is 2 times n plus 1 times n factorial times parentheses 2n factorial. This down here would be 2n plus 2 factorial, and then times 2 times n factorial. So already I can see that there's an n factorial which cancels. I think I bit off more than we can chew. Oops. So there's this and that. They cancel, right? And let me just point out that 2n plus 2 factorial downstairs this guy, we can expand how? This is 2n plus 2 times 2n plus 1 times 2n parentheses factorial, and there's still that 2 from the step above, all right? The reason I did that was so I can cancel the 2n factorials, like so. And then what do we got? We have, oh, the 2's cancel, right? And what you're looking at is n plus 1 over, well, 2 times n plus 1 times 2n plus 1. You could actually cancel these n plus 1s if you like. And you get 1 over 4n plus 2, which goes to 0 as n goes to infinity. Sorry if I've written below the event horizon for you. The point is, yes, after we do the math, ratio test works. It succeeds. We are victorious in showing that the ratio goes to 0. Hence, what? Lambda is less than 1. That says that that series converges. All right? I will not be able to prove the remaining ones, but let me just tell you what I forecast is how we should think about it. I think you're okay for the first 3 terms on problem 6. Great. Do you guys have any intuition about this converge or diverge? I tend to think that this is divergent because I think 1 over log to the 10th power is still like not growing as fast as k. I could be wrong, but I don't think log grows that fast, and so I think this is like worse than the harmonic series. My intuition is that this diverges, but I could be wrong. We'll have to I'll have to think more about problem 6. Problem 7. So you guys think it converges? I tend to agree. And I'm not, maybe this is an integral test problem. We could integrate x squared e to the minus x, right? So I think one tool you could use here would be integral test. I'm not sure. Oh, you guys were trying for the root test? That might not be a bad path. So then you were faced with the question is what is k to the 2 over k limit to, right? So we should talk more about this one. Problem 8, converge to 0. Again, that doesn't matter. Like if the term goes to 0, that just tells you it might converge. It doesn't, this is not enough. This is like the p equals 3/2 series. So I'm pretty sure you could use limit comparison with, say, p equals 3/2 and get that this converges. I would say limit comparison with p equals 3/2. This one, yeah, I'm not sure what's going on here. But I believe maybe the kth term, the root test might be a good one here. If we look at the kth root of that, we get k over, oh, is the root test no help? I think that the root, it goes to 1. Is the root test inconclusive when it's 1? It is. The root test won't help us. All right, so in summary, we'll have to look more at problem 9, problem 7, and problem 6 in a future class. Okay, guys?